Hello, everyone. I'm going to be talking about some recent results on error correcting codes in the Ulam metric. This is joint work with Elazar and Kartik, both of them are here, and if I say anything incorrect, they can probably fix that. Okay, so let's start with some coding theory refresher. In this talk, by an error correcting code or a code, I'm going to mean a set C of strings of some given length n over some alphabet. The members of this set are going to be called code words, and the focus of this talk is going to be on a particular class of codes called permutation codes. In a permutation code, every code word is a permutation of the numbers 0 through n minus 1. So you can think of these permutations as strings of length n with no repeating letters over the alphabet 0 through n minus 1. And we're going to need this one piece of notation. We're going to denote by S sub n the set of all permutations of 0 through n minus 1. So the code that we have is a subset of S sub n. Okay. The next thing we need is some notion of distance on code words.
You have to share the screen.
It will go away automatically.
Okay, thanks.
Yeah. So as I was saying, we know what codes are. The next thing we need is some notion of distance on code words. And in our work, we looked at the Ulam distance, which is a natural notion of distance if you're working with permutations. So what is the Ulam distance between two permutations? The Ulam distance between two permutations pi and pi prime is the minimum number of symbol relocations required to transform pi into pi prime. So let's look at an example. Let's say pi is this permutation and pi prime is the permutation, this one. So I just wrote pi here one more time. Let's say I take this one and I decide to place it here. And let's keep track of all the symbols we're touching with the color red. We're going to need it later. So that was one relocation. Now let's take this 3 and place it here. We're again marking 3. And finally, if you take this 6 and place it here, you can see that now this permutation has turned into pi prime. So how many symbol relocations did we need? So we can just count the number of red symbols. We required 3 relocations. So the Ulam distance between pi and pi prime is 3. There's another observation that we can make here, which is if you look at all the symbols that we did not touch, which means the black symbols, these are the untouched symbols. The relative order of these symbols must be the same in both pi and pi prime. Otherwise, we would have needed to touch them. So these black symbols, they must form a common subsequence of pi and pi prime. Moreover, since we're trying to minimize the number of moved symbols, we're trying to minimize the number of red symbols, so we are trying to maximize the number of black symbols. So actually, these black symbols, they form the longest common subsequence of pi and pi prime. So we have this following very nice fact, which says that the Ulam distance between two permutations pi and pi prime is n minus the length of their longest common subsequence. Okay. Or in other words, if you want to make the Ulam distance large, you want to make the LCS small and vice versa. Okay. Some more definitions. The distance of a code is the distance of a code C is the minimum Ulam distance between two distinct permutations. Okay, and the relative distance is what you get by normalizing it. So if delta is the distance, delta over n is the relative distance, is a number between 0 and 1. And the rate of a code, the rate of the code C is the largest number r, such that the size of C is at least n factorial to the power r. So if you stare at this definition for a while, you will realize that this is a number between 0 and 1, and it's a measure of how many strings are there in my set C. Okay, so C is a set of permutations, so the larger it can be is n factorial. So if R is telling me how many strings are there. So yeah, the higher R is, the more permutations we have in C. However, the higher R is, the smaller the relative distance is, which makes sense, right? If you want to pack in a lot of permutations, you can't ensure that like every pair is far apart. And a code whose relative distance and rate are both constants that are independent of n are called good codes. So they're good in the sense that every pair is far apart and you still have a lot of them. So now that we have all the definitions out of the way, we can talk about what we did. So our contribution is the following. We gave the first explicit construction of good codes in the Ulam metric with the relative distance arbitrarily close to 1. Slightly more formally, you give me some epsilon, I'll give you an infinite family of permutation codes in the Ulam metric with relative distance at least 1 minus epsilon, positive constant rate, where this rate might depend on epsilon, but it does not depend on the length of the permutations, and efficient encoding and decoding algorithms. Okay. So does the result make sense? You give me any, yeah.
So infinite because you're not picking any yet?
Yeah, we're not picking any
Okay.
yet. So for every epsilon, I give you infinitely many n's.
Yeah.
So yeah.
What do you mean by encoding and decoding?
Oh, by encoding and decoding, the way you can think of it, you have this set which contains a lot of permutations. You give me a number, say I can give you the ith permutation quickly. Also, and I'll talk about what decoding means later. But by encoding, I mean this. It's not just some set that exists. If you tell me, if you ask for a permutation, I can supply a permutation to you.
But if I give you a permutation with a bit noise, could you find the
Yeah.
original one?
Yeah, that's what I mean by decoding. If you give me a permutation which is close to some code word, I can find you the code word that is closest to it. Okay. So before we talk about how we did it, let's talk about some related work. So the earliest work on codes in the Ulam metric can be found in a paper by Levenstein back in 1992. He gave codes with distance 2 an optimal rate, meaning if you want every pair to have distance at least 2, you can't have more than this many permutations. In a much later work, Beam and others constructed codes with very small rate, consisting of only log n code words. So there could be n factorial many code words. They had very log n, very small number of code words with very high distance. Every pair is roughly n minus square root of n apart. But the first main systematic study of codes in the Ulam metric were done by this paper by Farnood and others, who gave many improved constructions with varying rate and distance trade-offs. And this is maybe the paper on codes in the Ulam metric. If you care about why these codes matter and if you care about practical applications, this is the paper you should look at. They also prove a bunch of theorems about codes. But what they couldn't do is construct good codes in the Ulam metric. The best they could do is the following conditional construction. So what they proved is this. They showed that, roughly speaking, if you give me good permutation codes in the Hamming metric, I can give you good permutation codes in the Ulam metric. And there is some loss in the distance. So if you start with a code with distance delta, relative distance delta, what you get out of it is a code with relative distance delta over 3. Okay. So if you want to create good codes in the Ulam metric, and if you want to use this framework, you need to first construct good permutation codes in the Hamming metric. But this itself was an open problem up until very recently. Good permutation codes in the Hamming metric were only recently constructed by Gulreich and Richterson. So you could now combine their result with the 2013 result and get codes, right? But if you look at this, if you combine these two, you can't get codes with relative distance better than 1/3, because delta is a number between 0 and 1. So if you do delta over 3, you can never get better than 1/3. So what we did is we overcame this barrier. And now let me tell you how we did it. So on a high level, our construction is as follows. You have this shuffling procedure. You start with the identity permutation, and you shuffle it to get a new permutation, and that is going to be our code words. That is going to be one of our code words. And this shuffle box takes in another thing called a shuffler sequence, and this shuffler sequence tells us how to shuffle the identity permutation. Okay, so you get one code word for each shuffler sequence. So what are these shuffler sequences? Where do they come from? They come from some non-permutation constant alphabet code in the Hamming metric. So these are not, so these W's, they come from some code in the Hamming metric, and these are not permutation codes, and these are constant alphabet codes. This we know a lot about. We already, we know quite a bit about these things. So what we are essentially doing is using what we know about codes, error correcting codes, and using them to construct codes in the Ulam metric. So this is the high-level idea. So in a little bit more detail, we're going to fix some constant q and let n be any power of q. We're going to need two ingredients. The first ingredient is a ground permutation set G. This set G is going to contain a bunch of permutations. How many of them? There are going to be p permutations. And these permutations are all going to be very small. They all have length q. So these are only small, constant size permutations. And there are p of them. And we'll pick p later. We also need a shuffler set S. And this shuffler set S contains a bunch of length n over q strings. And these are all p array strings. So they use symbols from 0 through p minus 1. And this p is the same as this p. Okay. So these are our two ingredients. With these two ingredients in mind, I can now describe our construction. Okay. So in this box, I have everything that you need to remember for this construction. You have n, which is the power of q. You have this G ground permutation set, and this set S, which is the shuffler set. Okay. So again, this entire thing, you can think of it as a L stage process. So n is q to the L. So you start with the identity permutation, which is pi 0. After stage 1, you get pi 1. After stage 2, you get pi 2, so on and so forth. Up until stage L, you get pi L, which is going to be a code word in our code. So how do you get from pi 0 to pi 1 and from pi 1 to pi 2, etc.? To get from pi I to pi I minus 1, you're going to need some wi, which is in our shuffler set S. And we're going to call that the shuffler for stage I. So say you have pi I minus 1, which is the permutation at the end of stage I minus 1, and you want to generate from it pi I, which is the permutation at the end of stage I. You're going to have to use this wi, which is the shuffler for stage I. So what does this shuffler do? So each symbol of the shuffler specifies how to shuffle the contents of some group of locations in pi I minus 1. So you have pi I minus 1, you want to shuffle some symbols around to get pi I, and this wi tells you exactly how to do that. So more details now. So before I can describe you the specific details, I need to do some sort of naming convention. So you're going to name each location in our permutations by their base Q representation. So these permutations all have length n, and n is q to the L. So every location has a name that is a length L string over the alphabet 0 to q minus 1. So every location is now a length L string. The leftmost location is all zeros. This one is all zeros followed by a 1. And the last one is LQ minus 1, right? So these are all named by their base Q representation. So say you're in stage I. So you already have pi I minus 1, and you want to make pi I, and you already have this shuffler wi. What you do is you group or color locations. How do you color locations? Every location whose names differ in only the ith symbol are going to be put into a group. Okay. So if you look at this picture, all the red locations, they are in the same group, because if you look at their names, it depends on what value of I we're working with, but if you look at their names differ in only the ith location, in the ith symbol. So the red locations are one group, the green locations are another group, and the blue locations are another group. Okay, so does the grouping make sense? So you're coloring location based on their names, and two locations are in the same group, or they receive the same color if their names differ in only the ith symbol. So if you delete the ith symbol from their name, it should be the same. If they're the same, they're in the same group. Does that make sense? Because this is like the main thing here. Okay. So the question is like how many, for the first question is how many locations do we have in each group? If you think about it, you're in the same group if you differ in only the ith symbol, and there are q possible choices for the ith symbol, so there are q possible locations in a particular group. So how many groups there are there? Like these groups form a partition of the location. So if you have q locations in each group, you'll have n over q groups in total. Okay, so you did this coloring. You have n over q groups. Each group has q locations in them. Now you look at the shuffler, and recall the shuffler itself has length n over q. So what you can do is construct a one-to-one correspondence between groups of locations in pi I minus 1 and locations in pi I. So you'll have a red location in the shuffler, you'll have a green location in the shuffler, and a blue location in the shuffler. Okay, does that make sense? So the number of groups you have is exactly the same length as the shuffler. So every location in the shuffler has a corresponding group associated with it. So, and also if you look at each symbol of the shuffler, recall that the shuffler is a p-ary string. So each symbol of the shuffler is a symbol from 0 to p minus 1. So now you go back to this ground permutation set, and it tells you what to do with that particular group. So if you want to know how to shuffle all the people in the red locations, you look at the red location in the shuffler. It's going to give you some number from 0 to p minus 1. You go inside G, and you pick the corresponding permutation, and that permutation tells you how you want to shuffle around these red people. Similarly, if you want to figure out what to do with the green people, you look at the green location in the shuffler. That tells you which permutation to select from G, and then you shuffle all the G people, all the green people, and similarly for all the blue people. Does the construction make sense? More or less. Okay. So, of course, like you can do this construction with any GNS, but if you want to ensure the desired rate and distance for C, you will have to choose GNS properly. So this is like a slide with all the parameters. I wouldn't stare at it too much, but I will say some stuff and like why certain choices were made. So we want G, the size of G, to be like not too small. So the size of G could be potentially as large as Q factorial. We just want it to be like Q to the epsilon G for some constant epsilon G, where epsilon G is in 0, 1. What's more interesting is the following property. For every permutation in G, we want, like every pair of permutations in G, we want their LCS to be very small. Okay, so you think of this ground permutation. You have a bunch of ground permutation set. You have a bunch of permutations. You want every pair to have very small LCS, or in other words, you want G to be in a code in the Ulam metric with very high distance and small but non-negligible rate. So how do you find such a G? Just remember that Q is constant, so you can just brute force to find such a G. And such a G always exists. So the idea here is, the upshot here is, G needs to have enough permutations, and every pair of permutations in G need to be like quite far away from each other. And what about S? S needs to be very large. So the maximum size S could have is like P to the N over Q. We need the size of S to be at least P to the N over Q to the RS for some constant RS. So S needs to be very large. Also, elements in S need to be far away too, but in Hamming distance. Okay. So what we want to ensure is we want to ensure that S has relative Hamming distance, at least delta S for some constant delta. And we know many such constructions. This is the code in the Hamming metric, and we know how to do this. So many constructions known. We can choose whatever. So we will make a choice depending on what we want later. And you can stare at these parameters for a while, but you can ask why these parameters and why these choices were made. On a high level, what is going on is, you know that G already has large Ulam distance, right? You want to somehow lift the distance of G, which is already very high, to C using S. And you also want S to be large to ensure constant rate. Okay? So that includes the construction. I'll probably not have enough time to talk about the analysis, but I do want to talk about what parameters we achieve. So let G and S be sets satisfying the properties I just mentioned. Then C has rate at least this, and relative distance at least this. Again, don't stare at these too much. What I want to say is, if you look at the relative distance, I did promise that we're going to get distances arbitrarily close to 1. The way you do it is, so if you give me an epsilon, I want to make the relative distance 1 minus epsilon. The way you do it is making Q sufficiently large, but still a constant. And if you look at the rate is again a constant as long as Q is a constant. So whatever promises I made, I can fulfill them. And maybe in the last few minutes, I can very quickly sketch why this works. So let's talk about the analysis. So the claim is, if you look at distinct permutations in my code, they're going to have small LCS. And what is the reason? The reason is as follows. So if you pick two distinct permutations, pi and pi prime, in my code, we must have used different shufflers during some stage to generate them. Otherwise, they wouldn't be different. Let I be the first such stage. And the claim is that the resulting permutations at the end of stage I, pi I and pi prime I, they're already forced to have small LCS. So you have pi and pi prime, they're different. So you must have used different shufflers. Let I be the first stage where you did something different. The claim is, at the end of that stage, you already have very large LCS, very small LCS. And furthermore, this cannot be undone. LCS lengths can only go down in subsequent stages. So that is probably all I'll say about the analysis. For the rate, I want to say that the rate is high because the number of shuffler sequences is high. You just need to count the number of shuffler sequences. And S being large itself ensures that the number of shuffler sequences is large. So the size of the code that we have is also large. We have high rate. And decoding, I will not have enough time to talk about it at all, but I will state the result. It says that if you give me some permutation with the following guarantee that there is another pi star in my code that is close to pi, then there is a polynomial time that takes pi as input and outputs pi star. And not surprisingly, this decoding algorithm uses the decoder for S as a black box. Okay. So yeah, that's probably all I want to say about our codes. Maybe now, so I can now answer questions if you have any.
Questions?
Yeah, can you tell us what the epsilon dependency is in the rate, and also what's the right bound if we don't care about explicit constructions?
Can you say that one more time?
So what's the epsilon dependency in the rate?
It depends on what you mean by epsilon, right? But what epsilon are we talking about?
The parameter which adjusts the...
Yeah, because we had actually a lot of epsilons floating around in many subsets. So we have to be a little bit...
1 minus epsilon.
Oh yeah, so yeah, that actually depends on like very specific choices of this shuffler set S. In our paper, we use like algebraic geometry codes, which gives you like the epsilon. It's like 1 minus 1 over poly q is this epsilon. So as you make q larger, like epsilon is epsilon is 1 over poly q. Does that make sense?
Yeah, but like, what do you want to set Q to be?
So depending on like what you want epsilon to be, so you give me some epsilon, say 0.1, I'll give you a large enough q for which this works. So like whatever polynomial I have, so I have, the distance is 1 minus 1 over poly q. So I want 1 over poly q to be epsilon. So you give me an epsilon, I'll choose a q that makes it equal to, that makes 1 over poly q equals epsilon. Does that make sense?
Yeah. And also, like, what's the correct bound if we don't care about explicit constructions? Do we know that?
Like correct bound as in?
Again, like based on.
Okay, so if you take a pair of random permutations, they have like very high distance. Like they did, like it's like n minus square root of n. So asymptotically speaking, the distance is 1. So I think probably you can do better than what we have here, but I don't know how to do it. So it should be like distance 1. Distance 1 should be achievable, I think. Yeah.
With the rate close to
Any more question? Okay, so let's say thanks. Oh, there is a question? There is a question, Guja.
Yeah, sorry. So, if I understand it correctly, there is a whole together the rate dependent on steps below. So we can get this at least level and
Can you say that one more time? I think I missed the first part of it.
the answer to the previous question was your rate.
Yeah.
Yeah.
Yeah. I'm not sure if, so I don't know. I don't know the answer to this. For now, like what we have, the rate does depend on the distance. So if you want to make the distance very close to 1, the rate does suffer. But maybe there is a way to do this. I don't know how.
Singleton bound. You can't really get too much.
Yeah. So what do you want to say? Yeah. So Karthik is saying there should be an argument based on the singleton bound, which says that you can't have both rate and distance be 1. So there can't be like, there should be some sort of dependence right here.
Okay, so if there is no more questions, so let's thank Mursalin again.